Basic definition of algorithm in mathematics is step-by-step procedure to solve a problem. Algorithms are basic and most important area in a writing and error-free programs. Figure 1 illustrates flowchart of a computer algorithm. One of the most essential thing to remember is that there can be various algorithms for the same problem, but some algorithms are much better than others. Technically, algorithm and programs are actually not the same thing. They differ at the level of precision. It is often expressed loosely defined format called pseudocode, which matches programming language closely, leaving out specific details that can be added later. Pseudocode doesn't have hard and fast rules about commands, but it is halfway between an information instruction and specific program. A computer algorithm is a set of instructions that a computer follows to solve a problem or perform a task. Algorithms are a fundamental part of computer science and are used in many different areas, including data processing. Algorithms are used to process data and perform calculations. Automation. Algorithms are used to automate tasks and systems. Security cryptography. Algorithms use encryption and decryption to protect data. Navigation. Algorithms are used in navigation systems to calculate the best route. Search engines. Algorithms are used in search engines to help users find information. Music streaming. Algorithms are used in music streaming services. Algorithms. Their meaning in computer science. In computer science, an algorithm is a list set of instructions used to solve problems or perform tasks based on the understanding of available alternatives. Algorithms are more than just programming. They are specifications for performing calculations, data processing, automated reasoning, or decision-making, for example, non-exhaustive list. To this extent, it is necessary to understand what it means for an algorithm to be correct and to accurately solve the problem at hand. Here are 8 critical steps in the development of an efficient algorithm. Definition of the problem. Development of a model. Specification of the algorithm. Designing an algorithm. Implementation of the algorithm. Program. Testing. Why is it fundamental in computer science? Well, the answer is simple. Computers would not do anything without programs telling them what to do. Algorithms give computers step-by-step instructions to accomplish specific tasks and make decisions. In programming, there are many ways to solve a problem. However, the effectiveness of the available methods varies. Some methods are much better than others at giving accurate answers. Algorithms are used to find the best possible way to solve a problem based on data storage, sorting and processing, and machine learning. In doing so, they improve the efficiency of a program. Algorithms are used in all areas of computing because it is a fantastic way of automating computer decisions. Let's say you have to drive 200 kilometers to your vacation spot. After checking what the shortest route is, data sorting, how to avoid traffic based on previous or current data, data storage, or how the weather forecast may impact your driving, data analysis. The algorithm will give you the best route and your estimated arrival time. Data structure and algorithms are good friends in computer science, machine learning, decision-making. Computer architecture deals with the design of computers, data storage devices, and networking components that store and run programs, transmit data, and drive interactions between computers, across networks, and with users. Computer architects use parallelism and various strategies for memory organization to design computing systems with very high performance. Computer architecture requires strong communication between computer scientists and computer engineers, since they both focus fundamentally on hardware design. At its most fundamental level, a computer consists of a control unit, an arithmetic logic unit, ALU, a memory unit, and input-output, I/O, controllers. The ALU performs simple addition, subtraction, multiplication, division, and logic operations, such as OR and AND. The memory stores the program's instructions and data. The control unit fetches data and instructions from memory and uses operations of the ALU to carry out those instructions using that data. The control unit and ALU together are referred to as the Central Processing Unit, CPU. When an input or output instruction is encountered, the control unit transfers the data between the memory and the designated I/O controller. The operational speed of the CPU primarily determines the speed of the computer as a whole. All of these components, the control unit, the ALU, the memory, and the I/O controllers, are realized with transistor circuits. Linked to the I/O controllers are secondary storage devices, such as a disk drive, that are slower and have a larger capacity than main or cache memory. Graphics and visual computing is the field that deals with the display and control of images on a computer screen. This field encompasses the efficient implementation of 4 interrelated computational tasks: rendering, modeling, animation, and visualization. Graphics techniques incorporate principles of linear algebra, numerical integration, computational geometry, special-purpose hardware, file formats, and graphical user interfaces, GUIs, to accomplish these complex tasks. Brain cancer, magnetic resonance imaging, MRI, brain cancer, magnetic resonance imaging, MRI. An image produced by magnetic resonance imaging, MRI, of a human brain affected by cancer. The bright blue area indicates that the cancer spread to the occipital lobe, lower right. Applications of graphics include CAD, fine arts, medical imaging, scientific data visualization, and video games. CAD systems allow the computer to be used for designing objects ranging from automobile parts to bridges to computer chips by providing an interactive drawing tool and an engineering interface to simulation and analysis tools. Fine arts applications allow artists to use the computer screen as a medium to create images, cinematographic special effects, animated cartoons, and television commercials. Medical imaging applications involve the visualization of data obtained from technologies such as X-rays and magnetic resonance imaging, MRIs, to assist doctors in diagnosing medical conditions. Scientific visualization uses massive amounts of data to define simulations of scientific phenomena, such as ocean modeling, to produce pictures that provide more insight into the phenomena than would tables of numbers. Graphics also provide realistic visualizations for video gaming, flight simulation, and other representations of reality or fantasy. The term virtual reality has been coined to refer to any interaction with a computer-simulated virtual world. A challenge for computer graphics is the development of efficient algorithms that manipulate the myriad of lines, triangles, and polygons that make up a computer image. In order for realistic on-screen images to be presented, each object must be rendered as a set of planar units. Edges must be smoothed and textured so that their underlying construction from polygons is not obvious to the naked eye. In many applications, still pictures are inadequate, and rapid display of real-time images is required. Both extremely efficient algorithms and state-of-the-art hardware are needed to accomplish real-time animation. For more technical details of graphics displays, see computer graphics. Human-computer interaction. Human-computer interaction, HCI, is concerned with designing effective interaction between users and computers and the construction of interfaces that support this interaction. HCI occurs at an interface that includes both software and hardware. User interface design impacts the life cycle of software, so it should occur early in the design process. Because user interfaces must accommodate a variety of user styles and capabilities, HCI research draws on several disciplines including psychology, sociology, anthropology, and engineering. In the 1960s, user interfaces consisted of computer consoles that allowed an operator directly to type commands that could be executed immediately or at some future time. With the advent of more user-friendly personal computers in the 1980s, user interfaces became more sophisticated so that the user could point and click to send a command to the operating system. Thus, the field of HCI emerged to model, develop, and measure the effectiveness of various types of interfaces between a computer application and the person accessing its services. GUIs enable users to communicate with the computer by such simple means as pointing to an icon with a mouse or touching it with a stylus or forefinger. This technology also supports windowing environments on a computer screen, which allow users to work with different applications simultaneously, one in each window.